Okay, I have two problems, I guess, related to centripetal force. Again, it's a force that will be pushing, or I mean, not pushing, but pulling the object towards the center of that circular motion. Okay, this force is just present if the object is moving in a circular manner. It maintains a circular path due to the centripetal force. It could be forces like static force or applied force, gravitational force, tension force, or even normal force. They will act as the centripetal force, pulling the objects towards the center. And it also follows the so-called centripetal acceleration. Okay, this blue arrow here in our diagram, there's an animal, an unknown species of an animal running around the curve. So if that case, we have the static friction between the feet of this creature and the ground. Okay, and the centripetal force now is our friction force in this case. Okay, the same direction. If you look at the image here, our centripetal force, it's the black arrow here. That's represent our centripetal force, or FC. The blue arrow, the same direction with the centripetal force, that's our um, centripetal acceleration. And we have this orange arrow, that's the vector of velocity, or that's tangential velocity. That's the the original motion supposedly of the object. Without the centripetal force, this particular species or creature will be moving in a straight line, tangent to that circle. Okay, so we have a narrative here. The narrative goes like this: some species of animals can run a 150 diameter. Let's be careful because we have diameter here as our given. I'll put it this way. Diameter, it's 150 meter. It's from this point all the way to this point here. Okay, that's the 150-meter diameter. And then another thing, this creature can turn at constant speed. Okay, constant speed because we're dealing with uniform circular motion, meaning uniform circular motion, speed is constant all throughout the motion. Okay, so our speed or velocity, that's according to the problem, it's 8 meter per second. And we need to figure out, according to the problem, let's figure out the centripetal acceleration, or this blue arrow here in our drawing. We need to find the value of the centripetal acceleration of this creature running at 8 meter per second speed. Okay, the speed direction, or the speed vector, it changes if ever this creature is at this point already. I will just represent it by a dot or tiny circle. And if you will try to uh, draw the vector of our velocity at that point in time, it must be like moving in a curvature, so it must be in straight line like this. So if you look at the position here, it's going north. right? Somehow like north, going there. And then there, the other direction, the new direction is not north at all. Okay? So it changes direction. So the object in this case is accelerating towards the center along with this the centripetal force. We call it specifically as the centripetal acceleration. We need to find it out. How to find centripetal acceleration? This time, let's have the formula to get the centripetal acceleration. Okay, again, since the velocity is changing, the velocity vector or the tangential velocity is changing when the object is moving all throughout the curve or in a circular manner or circular path. Therefore, the object is somehow accelerating due to that change in direction of our velocity. Okay, and yeah, I will be presenting to you now the formula to get the acceleration, specifically the centripetal acceleration. So we have this formula. AC, that's our centripetal acceleration. That's equivalent to a very simple formula. All we have to do is to divide the velocity squared over r, radius. Okay, if you look at the given, we have this diameter here. And diameter is the whole, not the whole, but the line segment from this point passing through the center of that curvature and to this the other point. That's the diameter. But when we say radius, it's just half of diameter. So we will just have to divide we will just have to divide 150 divided by 2, because this is 150 diameter and our radius is just half of it. So we can put it this way. This will be our, from the center, this is one radius, let's say r sub 1, and we have also another radius here. So we're going to be our r2. If we will add this r1 and r2, we can get 150 as the diameter. So what's half of 150? Okay, 150 divided by 2, we have 75. Don't forget the unit meter. So our R1 is 75 meter, and the other radius here, that's another 75. All in all, it will be 150 meter as a diameter. So we already have the R. This is the value of our radius R, perfect for this variable here. Okay, now the velocity is given in the problem. It's 8 meter per second. That's constant when we're dealing with uniform circular motion. Speed is constant all throughout the curvature or the rotation or the revolution or when the object is moving in a circular manner. Okay, so let's do the math now. It's very easy. The value of our velocity here, v, is 8 meter. So that 8 meter, we will be substituting that one in our V formula. So instead of writing V, we will make it 8 meter per second. Okay? 8 meter per second, that's the value of our velocity in a given problem. But don't forget, we need to, okay, hold on. We need to square 8 because that's the formula. And then our R, we have it here, 75, that's half of 150, the diameter. We will divide it by 75 meter. What's next? Let's square the uh, velocity or speed here, or we will just have to multiply 8 by itself. Remember, when you have 8 squared, it means 8 times 8. Okay? So 8 times 8, that's 64. Do not put it this way, like if you will encounter 8 squared and then you will write 8 times 2 and 16, that will gonna be very wrong. Okay, because when we say 8 squared, we need to multiply 8 by itself twice, so you will have 64. Okay, so 8 times 8 is 8 times 8, it's 64. And the unit, we will also do the same. Since we need to square what's inside the parenthesis, we need to square out units as well. Okay, so as you can see, we have two, we have meters there. We need to multiply meters twice. And meters times meters, that's meter squared. And we also have second inside. Okay, so second times second, that's second squared. So we can write it as 64 meters squared over second squared. Okay, don't forget, we will still be dividing it by the radius 75 meter, and we can cancel unit now. All right, we have 1 meter here. We can cancel it out, and this is 2 meters. I mean 2 meters because we have 2 meters exactly. And we cancel 1 below. We can also cancel 1 here. So we have remaining 1 meter unit. Or as easy as you have squared here, just delete, sorry, that's cancel the square, meaning you have 1 meter left. And we will divide now. 64 divided by 75, the quotient or the answer is 0.85. And we have repeating threes along the way. So we can just have to let two sig figure or significant figures, 8 and 5, and the remaining unit, we have meter per second squared because we cancel meter already, and the unit is meter per second squared. It makes sense. This will be our answer. This is the centripetal acceleration of this creature running at 8 meter per second within this curvature. Okay? Uh, Remember, meter per second squared, that's the unit of acceleration. And we're dealing with centripetal acceleration. So that's the answer for this problem. Thank you for listening. And I still have a lot of problem later. Yeah, we have another problem here. I will change the uh, page. All right. So we have these two curvatures. The first one, the radius is provided is 25 meter, and the other radius is much larger. It's 35 meters. So let's try to find out because we have a North Star here. Longer radius means blank. We need to supply it with the correct answer later. The longer radius means blank centripetal acceleration. So what will going to happen if radius are or the radius is longer? What will going to happen to its centripetal acceleration? The blue line here, it represents our centripetal acceleration, and the black arrow going to the center, that's our centripetal acceleration. It's a car moving at 25 meter per second speed. So in dealing with uniform circular motion, our speed is constant. So it's 25 meter per second. And if the object will be here, it's still 25 meter per second. If the object's still here, it's 25 meter per second. It's constant along the curvatures. Okay. Now, we will try to find out what's the uh, AC. AC stands for centripetal acceleration. Acceleration following the direction of the centripetal force, going to the center. So centripetal acceleration. Figure out the centripetal acceleration as the car moves, or if the car rounds a 35-meter curvature. So in this first curvature here, let's try to find out the AC. So you could still recall AC is just velocity squared over radius. What's the value of our velocity? It's very clear. I hope you're following. We will change V into this value. So V is 25 meter per second. Don't forget to square it out. Divided by the radius as it crosses on this curvature. So the radius here, it's 35. So we will divide it by 35 meter. And we will do the math. We will have now, since that's 25 squared, what to do? 25 times 25. 25 by itself. 25 times 25, that's 625. And then what are we going to do? What are we going to do with the unit meter per second? We will still do the same thing. So meter times meter, that's meter squared. So we can say it's meter squared over second times second, it's second squared. So that's second squared. So the answer in the numerator, it's 625 meter squared second squared. And we will divide, don't forget, we will divide it by 35. But before that, we can cancel unit. We have 1 meter here, get rid of it, and you still have 2 meters here because we have meter squared. Just get rid of the squared uh, number there. Okay, so the remaining unit, it's meter per second squared. That's the unit of acceleration, so it makes sense. 625 divided by 35. The answer is, hold on, the answer is 17.85, and we have 714, and then there's still a lot of number. Don't forget to have the unit meter per second squared, or we can simplify it by rounding it off. So let's say we will end in this figure. So 5, look at the number to the right, it's 7. So if you will have 7 above, plus 1. If you will have 4 below, retain the number. So in this case, we have number 5 as our target. Look at the number beside number 5 to the right. It's 7. So 5 above, we will have plus 1. So our answer will be approximately 17.8. Instead of 5 plus 1, you will have 6 meter per second squared. This is the acceleration of this curvature here, 17.86 meter per second squared. Let's try to find out the centripetal acceleration if the car is uh, in this position. Let's say that's the car. So the centripetal force is always pointing towards the center along with our AC. And we need to find what's the value of AC in these shorter radius. Okay? What about, this is the question, what about What about if it rounds? If it rounds a curve of 25 radius. Okay, so this is our radius, the shorter one. Now, same formula, it's AC, centripetal acceleration, v squared r. And our velocity in a uniform circular motion, velocity or speed is constant. Don't forget that one. So it's 25 meter per second squared. So still not squared. I'm very sorry. It's meter per second. The velocity is also the same here. It's 25 meter per second. Okay, so we will substitute now. Our V is 25 meter per second, and then we have squared here. Over our radius now, we will be uh, choosing 25 meter, the shorter one. And let's do the math. We will fix the numerator, the above figures. So again, like what we did earlier, we have squared sign there. So 25 is inside. 25 times 25, not 25 times 2. It's very wrong. Just 25 times 25, the answer is 6 to 5. And the unit inside our parenthesis, we will still do the same. Meter times meter, we have meter squared. Over second times seconds, we have second squared. So that's the unit. So our answer is 625 meter squared second squared divided by 25 meter. The quotient is 25. And don't forget, we can cancel this meter here. And we have 2 meters unit here. We can just omit the squared. So you will have meter per second, unit of acceleration, since we're dealing with centripetal acceleration. So the unit is meter per second squared. This is now the centripetal acceleration when the object is rounding on a shorter radius. Okay, if you notice, it's 25. It's lesser than 35, obviously. So our North Star, the longer radius, what will gonna happen to our centripetal acceleration at uh at 35? This is longer than 25. Look at the centripetal acceleration. It's just around 17.86. But if the radius is shorter, like 25 in the next uh, curvature, so the centripetal acceleration is 25. It's higher than the previous one. So longer radius means uh, lower. Is it good or small or lower centripetal acceleration? Meaning to say, shorter radius equal to high AC.